All right, so we might start with some introductions. So welcome, everybody. It's our great pleasure today to welcome a delegation from Fukushima Research, Education and Innovation Institute. We have the director for the field of robotics, Dr. Nonami Kenzo, who is also Professor Emeritus at Chiba University. We have the vice director for the field of robotics, Dr. Matsuno Fumitoshi, who is also Professor Emeritus at Kyoto University and Professor at Osaka Institute of Technology. And we have the unit leader for Haptics research, Dr. Ohnishi Kouhei, who is also a project professor at Kouhei University. So I think this is, compared to most of our seminars here, I think we've got more speakers than usual and also more sort of gift bags and loot than usual. So that's pretty special, I think. So we've got the outline here today. I think it looks like a really exciting program. This group is very well known for robotics in harsh environments. So we're going to hear from the group about some of the work that they'll be doing, and there'll be time for Q&A afterwards as well. So without further ado, I will hand over Dr. Kenzo, would you like to start?
Thank you for coming and joining us today. I'm a director field of robotics, F-REI. The F-REI Fukushima Institute for Research, Education and Innovation was founded 2 years ago. Very new national research institute. Okay, and we are now preparing the harsh environment F-REI challenge, which will be happening this October, October 10 to 12, 3 days challenge, which includes harsh environment drone challenge. This is my background. And the second one is plant challenge, disaster plant challenge. The third one is simulation challenge. And the fourth one is STM, standard test method challenge. We have 4 kinds of challenge. So visit of our mission is to gather the excellent team from from University of Sydney group and some Singapore, Taiwan, USA, and India. Now we are visiting to get together the excellent team to join the this challenge. Okay. This is one visit mission. The second one is we are now the new research institute. I think up to 5 years later, in 2030, almost 500 researchers gathering all together in the Fukushima area. Fukushima area, as you know, we had a very tragedy accident, nuclear power accident, almost 14 years ago. And also, we had a very huge earthquake. We had, so it's called the Great East Japan earthquake. So almost more than 20,000 people died by this earthquake. Okay, so in that serious and very tragedy accident, the robotics is very, very useful. So we are now developing advanced robots or intelligent robots aggressively right now. So let me show you the briefly about the F-REI's overview. Okay, this is unfortunately this is a Japanese edition.
福島、東北の復興を実現するために、日本の科学技術力、産業競争力の強化を牽引し、さらなる経済成長や国民生活の向上に貢献するために、福島の力、世界に冠たる創造的復興の中核拠点を目指す F-REI 福島国際研究教育機構。復興の地福島に拠点を構え、福島からここ浜通りから日本と世界の課題解決に貢献していきます。2023年4月、福島県浪江町のF-REI本部において、岸田内閣総理大臣をはじめ多くの方にご出席いただき、F-REIの開所式が催されました。F-REIは福島復興再生特別措置法に基づき国が設立した全く新しい法人です。それではF-REIの4つの機能を紹介します。
F-REIの持つですね、ミッション4つの機能というのは、1つはしっかりした世界最先端、世界水準の研究を実施すること、そしてまた2つ目はその研究成果を用いてですね、産業化ですね、地域に産業を巻き起こすこと、3つ目は人材育成であります。先ほど申し上げたですね、研究成果の社会実装を通して地域に人材をしっかりとですね、定着するように育てていくというのが大事な使命だと思っております。また4つ目はですね、司令塔機能というふうに言われてますが、被災後ですね、浜通りあるいは中通りにですね、国の研究機関を中心にですね、いろんな形で今まで先行的な研究がなされてきております。それらの成果を大切にしながらもですね、やられていた研究分野をですね、しっかり全体を取りまとめる形でですね、F-REIがですね、統率機能を、発揮して全体としてですね、日本の研究力のその成果、研究の成果がですね、最大になるように我々は皆さんと一緒にですね、統括していきたいと、こんなふうに思ってます。
F-REIでは以上4つの機能を一体的に発揮してまいります。これらのうち研究開発機能について、F-REIでは福島の優位性が発揮できる5分野を基本に取り組んでいきます。過酷環境下で機動性を発揮するロボット、ICT 技術とロボット技術の融合による自律機能に関する研究開発、長時間飛行、重量物を搭載可能な高性能ドローンの研究開発などに取り組みます。スマート農業やカーボンニュートラルなどを通じた地域循環型経済モデルの構築を目指し、超省力、低コストな持続性の高い農林水産業に向けた実証研究などを行います。福島を世界におけるカーボンニュートラル先駆けの地とするため、水素エネルギーネットワークの構築やネガティブエミッション技術などの研究開発を進めます。オールジャパンの研究推進体制の構築と、放射線科学に関する基礎基盤研究や RI の先端的な医療利用、創薬技術開発に取り組むほか、超大型 X 線 CT 装置の開発など、放射線の産業利用を目指した研究開発に取り組みます。自然科学と社会科学の研究成果などの融合を図り、原子力災害からの環境回復、原子力災害に対する備えとしての国際貢献、さらには風評払拭などにも貢献します。また F-REI を核とした復興まちづくりの効果検証研究を実施し、活力ある地域づくりにつなげます。これら5分野を基本に融合発展させながら、 F-REI は研究開発に取り組んでまいります。復興の地福島だからこそできる研究や社会実装を通じて、世界の課題解決に向けて取り組みを進めます。また F-REI は地域の市町村や企業などとの間でさまざまな形のパートナーシップで連携、 広域連携による効果波及を目指してまいります。さらにF-REIは6名のスペシャリストたちが先頭に立ち、さらなる飛躍を遂げていきます。
F-REIは2023年に始まり、2029年まで第1期中期計画期間として、当初の外部委託などによる研究実施から徐々に直接雇用、クロスアポイントメントによる研究開発へとシフトしていきます。2030年以降は第2期中期計画期間として、F-REIはさらに発展し、最適な研究開発体制、広域連携体制の司令塔機能を発揮していきます。
世界に冠たる創造的復興の中核拠点を目指すF-REI。世界でここにしかない多様な研究、実証、社会実装の場を実現し、国際的に情報発信していきます。復興の地、福島でしかできない、福島だからこそ果たすべき役割があります。福島を被災地から最先端の研究開発、人材育成の地へ。新しく始まるF-REIの取り組みにぜひご期待ください。F-REI福島国際研究教育機構。
First, I appreciate to hold this event by your Professor Manchester. Thank you so much. Okay. Let me introduce WRS World Robot Summit 2025 harsh environment F-REI challenge. Let me introduce. The WRS 2025 includes three kinds of event challenge. The orange line is futures convenience challenge. You know, there are many kinds of convenience store all over the world. And so futures, maybe mostly robots will working in a convenience store. So this is one challenge. The second one is green color. This is our harsh environment F-REI challenge. Okay, and the third one is the how to say the purple line. This is industrial robots challenge. We have three kinds of challenge. Okay? So now I'm focusing on this F-REI challenge. I mentioned already about the date, the October. This October 10th on Friday to 12th on Sunday, 3 days challenge. Okay. And it has 4 challenges. Okay. Harsh environment drone challenge. I will explain more after this. And plant disaster challenge, second one. The third one, simulation disaster challenge. Fourth one, standard disaster robotics drone challenge. We can say this is STM challenge, standard test method challenge. Okay. The deadline is this May 12th on Monday. You have much time, so yeah, completely. Okay, so you can access WRS 2025 by Google or Yahoo or something. You can access this page. So please put this entry. Okay, this is entry page. You can enter this entry button, and then you can see all of document in detail. So please access to this page. Okay, this is the cover page. So let me explain the HEDC, just some for HEDC, harsh environment drone challenge. There are many kinds of drone challenge in the world. DARPA challenge, and the Middle East challenge, and so maybe in Australia, your country, maybe you have some kind of drone challenge. Your country is very huge, mostly desert. So I think it's easy for flying, very good environment in your country. But unfortunately, in Japan, we have very small country, so many population. So it's not easy to fly. So we are looking for the flight site every day we're worrying about. So anyway, this challenge will be fly from takeoff and the landing site to the middle square, red square, you can see, almost 7 kilometer distance. So you have to fly. So totally 14 kilometers, more than 14 kilometers. And then this is a Fukushima robot test field. This is near our F-REI's headquarters. And by the way, just a half an hour drive. So this is 13 kilometers directly from the takeoffs and the landing site to RTA, robot test field. Okay. So we have 3 missions. Mission 1 and mission 2 is searching the rescue vehicle pass. And the mission 2, you have to read some character letters on the ground, and then you have to fly. You have to transport some supplies. And the mission 3 is you have to enter the building and search the victim, and then you have to make a 3D map as soon as possible. So I mentioned already the mission 1 is this is the rescue vehicle route search. The using a flying roll, very easy to the route search by drone. Very easy mission. I think first mission is very easy. Okay, but you have to submit the also map by using many photos, and then you can gather the one photos. Okay, I will explain more a little bit. The mission 2 is so you can see the 2 persons help sign, and you can search the letters, English letter like a water, medicine, or clothes, or food or something. So and then you have to transport such a request supplies. Okay, you can see the recognizing the letters painted on the ground at first, and the deliver supplies requested by rescuers by landing or dropping at the designated locations. Okay. The mission 3, this is a building, inside of building. So the mother drone will carry the kid's drone, small drone, and then you dispatch the small drone, and the small drone is going to the inside like this through windows or some door. So windows normally not so big, like below 1 meter wide. So small drone will be going inside, and the small drone will check the victims like this. This is a third mission, mission 3. And then, unfortunately or fortunately, this is a harsh environment drone challenge. So this radio wave relay system should be needed. Okay, to realize a safe and reliable operation. And you can use many drones, it's okay. We don't have a limitation of the number of drones. So many drones is much better than the small few drones. Okay? And you have to need radio delay relay system like this, because we have a very small hills, 30 meter high or 70 meter high like this. So this is one difficult mission. One of difficult mission. This is a takeoff and the landing site, like a runway. So you can use fixed wing also, because this is a takeoff side and also landing side. This is a top view. So you almost 100 meter wide and 500 meters long. And the mission 1 and 2, I have already mentioned about the mission 1 and 2. One is the rescue vehicle road search. Okay, and so mission 1 is left-hand side of this area. Okay, and the right-hand side is a mission 2 area. So you can search the letters on the ground, and then another drone will transporting some supplies requested by victims. Mission 3 is a 3-story building like this. This is a robot test field, inside of robot test field. So you can see the small windows. So you can go inside through this kind of small window. Very, very high hurdle, I think. So mission 3 is this. This is an overview of a robot test field out here. 1 kilometer long and 500 meter wide. So very wide area. So you can hovering or landing in this area, yellow circle and the red circle and so on. And the access route here, because we have a power line of high voltage power line. So you can fly over power line. So access route is shown here. So the right-hand side, this is a Pacific Ocean. So this is east side, this west side. So this is a schedule until the challenge. So I mentioned already, the deadline is May 12. May 12. So now almost end of February. So March 4th, the preparation for you. And after application, we are verify the all document, and we are going to submit the JCAB, Japan Civil Aviation Bureau. This is the JCAB. So JCAB will check, evaluate, and the all document, and then we can get the permission of flight. So this is maybe in Australia is the same process. Every country is same process. You have to submit the permission to get the permission to each country's civil aviation bureau. So this is the same one. And then October 10 to 12, 3 days challenge will be followed. So next one, this is the HEDC and the WRS F-REI challenge. Next step, I'm talking about the overview of robotics activities. We have 3 main scope. Key commissioning robots. This is very, very important because we had a huge nuclear power plant accident and the radiation scattered to Fukushima area. So many people escaped to another area, but almost 10% people returned to the hometown. 90% is still living in another area. So we have to build a new industry, such as previous talking about. So decommissioning robots, this is a quite important area. The second one is the disaster response robots. The third one is the forest robots. So we have a very huge, very important 3 missions. And I mentioned already about recruiting the researchers. So call for researchers. If you have you like Japan and Japan culture, and if you'd like to research in Japan with some another member, please apply this recruiting system. So anytime we are recruiting other researchers, and this is already, and the basic rectangular area. So we have the basic research, high mobility technology, fuel cell or hydrogen fuel cell, and so on. The second one is high intelligence technology, like autonomous intelligence and the swarm technology. The third one is function expansion technology, haptic teleoperation. Professor Ohnishi will talk about this one. And the high intelligence technology, the Professor Matsuno will present after this. And the disaster service for the standard and certification. Okay. So now we are myself and Professor Matsuno and Professor Ohnishi, Professor Tomitsuka. He is living in the US, UC Berkeley, very famous control engineers in the US. He is Japanese, of course. And third one, right hand side, he is unit leader, Professor Yama. He is leading a hydrogen-based fuel cell to implement drone to increase payload or long distance duration of flying. This is F-REI's this April, this robot test field joined the F-REI. So I'm showing this is a robot test field. So you can use this area if you are F-REI's researchers. Okay. And the subtopic is UAV, just small. This is a global drone market trend provided by let's see, DII, Drone Industry Insight, which is Germany's think tank. They searched the drone market, and then this is one trend. The increasing 7.8% increasing by every year. And this is three drone in the top 3 drones area, application area. So energy, 40%, construction, 12%, agriculture, 9%. And the methodology, mapping and survey, 34%, inspection, 25%, photography and filming, 10%. And this is a very interesting figure. Type, there are many kinds of job. So which job is more dominant? So in the US, drone hardware engineer is quite important. And the second one, passenger drone. And the software and the drone service delivery. Okay. So Germany, India, Australia. So your country serve both. So your country, according to the DII, drone industry inside, your country is mainly drone service delivery. And the second one is the drone hardware and the software and so on. So Japan is the bottom, mainly drone service and the drone hardware. Okay, so why we use drone? So because we can see this answer, the saving cost, saving time, improve quality, and improve work safety. So this is the 4 reasons to use drone. And this is there are many kinds of drone type: fixed wing, helicopters, VTOL, multi-copters, and so on. So this is a ratio. So top one, best one, top share is multi-copter, 40%. The second one is fixed wing, 27%. VTOL, vertical takeoff and land, 24%. Helicopter is 9%, below 10%. This is a power source. Electric-based drone is 65%. And engine-based drones, 21%. And hybrid, to generate electricity via engine. This is, we can call hybrid. So 11%. Sometimes the solar power, some 3%. This is a power source ratio by drone type. So multi-copter, almost electric-based drone. On the other hand, fixed wing is also a small fixed wing is also electric-based. But the fixed wing, large fixed wing is based on 70% engine. The helicopter, 33%. So as well. This is the top 10 maximum flight speed. Very small number. So I sent Professor Manchester. So please distribute to your colleague after this. This is also flight time. This is the top 10 ranking. Okay? This is top 10 ranking. I surveyed by myself. This is not DII, drone industry inside. No, I did. Okay, I took 2 years to survey. So this is a top 10 maximum flight speed and time. Camcopter from Austria, not Australia. Flex rotor from USA. This is a let's see, tail shifter aircraft. This is a payload. The big one is 350 kilogram, very big payload, which is Black Swan by Bulgaria, not the USA. Okay, this is Black Swan, Bulgaria. It's a very big, like a passenger aircraft, very similar to passenger aircraft, but unmanned system. No pilots. This is the maximum flight speed with electric only. So this is very famous wing copter in Germany. So after this, I will show you some finally three movies. This is our companies. I did a venture company, two companies. One is already IPO. The other one is now going on. So the second one, my venture company is moved. So I don't have a time, so I pick. So this is power line survey. You can see the power line, very high voltage power line, almost 500,000. Yes, 500,000 volts, very high voltage, commercial use voltage. We are now survey the damage area or no damage area. So we are classified the survey by this right. The next one is this is wire drone. So power supply is coming from ground generator. Okay, so this is so we can fly 2 days continuously, 2 days, 48 hours. So we can use this kind of wire drone for disaster area. Those telecommunication is very tricky. It's difficult. So we can set up this kind of wired drone with base station, cell phone base station. So finally, this is a fixed wing. You know, the ship is accelerometer or something, but it's very difficult. So thank you so much for your attention. Thank you.
Okay, thank you very much. So my name is Fumitoshi Matsuno from Fukushima Institute of Research, Education and Innovation. The title of my talk today is Beyond Living Things, Future of Biomedical Robots. So first question for you. Do you think a snake can climb up a tree? Yes. Oh, many people. Okay. Yes. Yes, a snake can climb a tree like that. So you can observe that the living snake can climb up a tree. It creates a fixed point on the tree by using a coiling motion. Then it lifts up a part of its body and establishes another fixed point to climb up a tree. Very interesting to read. So inspired by this movement, we design climb up motion by combining spiral and a rolling motion like that. The snake robot can move outside of a pipe with an obstacle. Some links are lifted to avoid an obstacle, shown in the middle group. And snake robot climb a natural growing tree with irregular shape outdoors. Okay. And it can estimate the shape of the tree by using only joint data and adapt to the environment change automatically. Okay. Friction condition is changed and the shape is not uniform. Very difficult to estimate the environment, but automatically adapt to the environment. Okay, another question. Do you think a snake can move sideways? Oh, man, okay. Some of you will know this snake. Yes, a living snake, sideways, can move sideways on desert. Very interesting. Okay. And our robot, snake robot can generate a similar motion as a living snake, sidewinder. This is a sidewinder, and our robot go sideways. Okay, and this is a current version of the snake robot we have developed. Its length is 2.5 meters and weight is 6, and it has 36 joints, very big number of the joints. At the joint, we introduce a pectinate shape to extend the mobile region of the joint. This is the pectinate shape, like that. Okay. And this movie shows the movement by chloragate on irregular terrain. An operator sent a command only forward or backward or turning. Very easy to operate. Okay. It's very easy to move the irregular terrain. And another question for you. Do you think a snake can climb a ladder? Oh, some of you. Yes. But I don't know. I don't know. But our robot can climb up a ladder like that. Yeah. It can climb up both vertical and inclined ladder. Note that the cable connected to the robot does not caught in the ladder. That's interesting. Okay? Yeah. So our robot. And this movie shows the movement of the snake robot transitioning from inside a pipe to outside. I think living snake does not have this kind of motion. Okay. And next, we will consider ant swarm behavior. Okay, social insect, for example, ant have many interesting functions, self-assembly, task allocation, and so on. Many cooperative transportation, many things. One key behavior of the swarm intelligence is distributed control strategy. For example, estimation of global information by only local interaction of individuals. Very interesting. And inspired by the ant swarm behavior, we consider navigation of swarm robots, leader follower navigation of the swarm. In the decentralized control strategy, each agent has local communication using local information. Each agent has its sensing region, like that. And this is a robot, and this is sensing region. This robot can detect these four robots, but outside the sensing region, this robot cannot detect these two. So it's a local information, and interaction of each agent with each is designed by introducing potential function. Okay, between the agent and agent, if the distance d is two agent distance is greater than some constant d, attraction force is generated like that. And if the distance of two agent is less than d, diffusion force is generated. And if the robot hit the obstacle, diffusion force is generated. And if we have a goal, so attraction force is designed to reach the goal. Very simple. And this is a fundamental idea to decentralized control law of the navigation of smart robot. And this movie shows a leader for navigation by decentralized control structure. This is a leader robot, and the leader robot knows the way to go, and others are forward. Forward don't know the which robot is leader, and also the way to go. And the first time, the leader leads the forwards, but in the second time, leader pushes forward. Forwards don't know the way to go, but leader pushes forwards, and they go through a very narrow area. Okay. And this movie is individual study within the school. It's a very complex behavior. So their behavior is not as simple as the separation, alignment, and the cohesion rule of the void model. Very, very complex. Okay. We have developed some bio-inspired robots. What are some useful application of the bio-inspired robot? That's a very important thing. As Professor Nonami said, as you know, the Great East Japan earthquake is complex disaster by not only earthquake and tsunami, but also Fukushima nuclear power plant accident. Due to the effect of the radiation, human cannot enter. So the robot should be used. Okay. This is we destroy the unit 1 unit buildings. And Amoka Fukushima Daiichi nuclear power plant unit 1 was made for inspection of its interior. Since wire UAV face movement restriction, a wireless access point was installed at the head of the snake wire snake robot. Okay, the wire snake robot can communicate with wireless drones. So this is some collaboration between the snake robot and the flying robot. And this.
Kimse başaramamış.
Okay, this movie shows the image from UAV inside the Unit 1 building in Fukushima. And this is a snake-like robot, and at the tip, the wireless access point is installed. And yes, so wireless UAV go into the deep area of the Fukushima building. This is a corporation cooperative inspection in unit one building at Fukushima by heterogeneous work.
Kimse başaramamıştı. Bu çekimler sayesinde en azından ayrıntılı bir biçimde
Living creatures has survived and being optimized by natural selection. This is flying snake. Our next target is flying snake. Okay. Based on our understanding of the behavior of living creatures, we can apply our knowledge to create robots to solve social and industrial problems, especially in harsh environments. Okay, thank you very much for your time.
Good afternoon, gentlemen, and thank you very much for accepting us. Thank you very much. Today, I would like to talk about haptic operation at the F-REI. My name is Ohnishi, and political professor of Kouhei. Okay, the contact task which human can do easily, but robot cannot do. Yes. Okay. Particularly, industrial robot is good for positioning, but not good for contacting. And mainly, industrial robot is based on position control or post control, either one. And if the robot is position based, then if the robot is doing some contact tasks, then maybe robot will break the target. And if the robot is force-based control, the robot will fall the target. And this side, the movie is robot based on position control, and it will break anything. And the right side is left side of the field debris picking up project, and that was maybe 4 years ago, and they grasped the pieces, but it's based on the force control. Then it is put up by the strings, and I think that they could go up, and I need to vibrating and attention. And then we hold down. So that is quite difficult for contact or grasp such kind of small things or fragile things. But if the force and tactile sensation is given to the robot, then the robot can do any kind of contact task. And in that case, real haptics is playing a very important role, because real haptics is a kind of technology to digitize and transmit and record the sense of touch. Okay, here we have 5 senses. Hearing was invented in the 19th century by Graham Bell, and it was telephone. And 20th centuries, visual sensation is transmitted by broadcasting. I believe that almost 100 years ago. But transmitting the sensation touch is quite difficult. And recently, it can succeed in digitize and transmit and record the sense of touch. And teleoperation and maybe or automation of the non-routine task and such. Most of them, including the contact task, require the sense of touch. And real haptics is mandatory for teleoperated robot. And this movie is a kind of the teleoperated robot, and robot can grasp such kind of the fragile things very successfully. And it's almost 10 years ago. But at first, we should know how to digitize sense of touch. Unless that, it's quite difficult for the robot to install. And it is necessary for robot to see or hear by digitizing visual audio sensation if possible, by camera or microphone if possible. And also, it is necessary to digitize sense of touch for contact task. But how to digitize sense of touch? That's an issue, long time issue. And any type of sensation, we have two types. One is intense, and the other is texture. For example, the visual sensation, okay, we have bright or dark. It is intense. When it is yellow or red or blue, it's a texture. With the same thing, in the same manner, in touch of sense, we have intensity and texture like this equation. It's quite interesting, very simple equation. And delta T is depending on the task. If you have, okay, all right. So this is the photo. You can touch it. But my finger is break. And also I cannot break this one because just after touching it, I can weak my force. But it is, as I said, non-conscious. Sometimes, any type of motion, your motion is that meaning non-conscious. So unless knowing non-conscious process, it is difficult for robot to grasp this kind of service like human. That's the issue. And the real haptics solves this almost completely. And according to recent results, intensity is here, and delta T depends on the task. Okay, grasping or pushing or bending. Delta T, maybe it's more than 30 milliseconds and less than almost 1 second. So a little bit wide. And if you can define this delta T, then you can break this 1, 2, 4 elements. And this is just like, the color is decomposed into 3 colors, R, G, P. Because in our eyes, we have the sensational cell just for sensing R, G, and P. So if you feel that it's purple, the kind of combination of these 3 colors, it's the same as our sense of touch. We have 4 components for our sensation. This one is more sensitive if the frequency is going up. And the second one is almost constant. So all of frequency range. The third one is, sensation is going down, if the frequency is going down. And the last one is just the DC component. And we have 4 receptors under our skin. As you know, one is Pacini corpus and the macular cells of substance, and 4 types of the receptors under your skin. For example, Pacini corpus is very sensitive to the high frequency, but low sensitive to the low frequency. And these 4 receptors are corresponding to these 4 components. But very interesting, these 4 components just the same as dynamic equation, so the motion equation. This is the inertia, and this is viscosity, and this is stiffness, and the H is load. Sometimes it includes friction. That's quite interesting because our 4 receptors do not know the dynamic friction at all. But according to our the long history of the what's that say, evolution, long time, and we get this kind of particularly for the animals level is higher than sensitivity higher, and for example, fish does not have this kind of sensation, maybe only this one. But for the human being, we have 4 receptors, and very interesting, this is corresponding to that evolution. Quite interesting. Okay, so this is a digitization of the sense of touch. And this is a master slave system. So sometimes say leader horror system or hand side or limb side systems. Or easily I can say just a master slave system. And master robot is operated by human. And remote robot can send a digitized sense of touch. Then the human can feed that and unconsciously feed like action command. And the remote robot can just follow the human with sensation of touch. Okay, but this is good. But one remote robot needs 1 person. So it's not automation. So it's not good for the industry. So this can be substituted by AI system like this. Okay, unconscious part is a human action data. Yes. AI needs always data. And by master slave system, we can record all of the action data is say every 0.2 milliseconds. And the amount of data can be obtained by the human motion by operating this human robot. So if she or he can do some task, according to task, we can have all of the motion data. So motion data can be obtained. And also we can have detailed sense of touch. So in these 2 data, we can construct a kind of AI system to have a good action command to the robot. So instead of this one, human being, we can substitute by this system by AI systems. And I skip the details, but we need 2 types of AI. But I can touch because of that time distribution. Okay, how to make a young haptics technology. This is very simple. This is a hand side device, and this is the side device. And we can employ 2 port systems like this. And to send sense of touch, substantially, we need two equations should be. One is here, it's action and reaction law, the simple one. Second is tracking law. But if you realize these two equations at the same time, you can hold down the singularity. Because if we divide first equation divided by mass, that means acceleration, sum of acceleration is there. If you derivate the second equation, the difference of the acceleration is there. That means all of the acceleration is zero. So the robot cannot do it. So that's a singular point. So how to avoid this singularity? It's very simple. First, we should have this equation. And with some delay, say 1 millisecond, the second equation. So we can avoid this singularity always. And this system is zero this length. For this hand side, and everything is acceleration based. And sum is the action and reaction law should be zero immediately. Then difference will be zero, but velocity control plus position control. And we can add some dynamics, and dynamics has always delays. First, first order delay or second order delay. And we can choose anyone. So we can choose, say, 1 second delay here. Then to equation substantially. And this can realize a very nice sense of touch. And this is just a demonstration. And this is the hand side that this side, and we can choose. And according, we have some kind of the some rule of thumb. In this case, almost 99% is the same. So if you have direct touch and indirect touch, it's almost the same. Secondly, this is another experiment, and you can understand what is going on. Okay, the distance is always there. That means the difference. And this one and this one, summation is zero. And if you do equation L1 and the forward one is at almost the same time, then you can calculate the force. You can calculate the very previous force of such. Okay, this is the experiments by the skeleton robot. And this is a universal robot. And it can have 4 cups, but only 1 cup is selected. And the robot can water inside the cup. The problem is that this robot is not so strong, so vibrating. This is a little bit probably it's not that. But we can do that. Such kind of systems possible. Second way is, sorry, we should say T service robot, but okay. This is a remote side and hand side, and this is the side. And you can see all the water is inside. And okay, coffee powder is on. And you can check temperature. You know, the 80 degrees is very good for the surface, right? And this is the temperature key. Okay, that's good. And it's cold a little bit. And okay. So, the empty cup is here. Okay, the rest of water is there. finally complete served to the paper cup. Paper cup is full, but it can. So the robot can adapt itself to the environment. Okay, I'm skipping very important matters because of the short of time. But we are seeking PhD research, and we can, we are having some research on these two items. One is various tasks by remote operation in harsh environment, and the second is automated robot for industry. And these 2 points are very, very important. And my talk is not limited to specific application such as taking off the debris from the reactor, but I think that this is possible to all of the industrial applications. So we need many big researchers in the play. Okay, thank you very much for your attention, and I agree that I hope that we have a nice time in the future. And my robot is proposing a toast to you. This robot, inside is aluminum, and outside is lava. Okay, thank you very much.
Yeah, so thanks to our three speakers for some fantastic presentations. Do we have questions from the audience? Great.
I think it was the first speaker was talking about the snake robots, and I noticed
Snake robots?
snake robots. None of your robots are soft.
Nano?
Soft. They're all hard 3D printed robots.
Yes.
So are you moving on to soft robotics? Would seem to be a better
Yeah,
option.
it's a one challenge. Yes. Soft material can be used for making a robot. So in that case, any application can soft robot can be applied to many harsh environment.
Yeah. But why did you use hard robots?
So easy to control.
Okay. Yeah. Fair enough.
And the control theory, depending control design suitable for that kind of rigid robot. But the soft robot is very attractive, but not easy to model and design the stabilized controller. So that's another point. But yeah, very challenging.
Yeah.
Thanks.
Thank you.
I have a question about the snake robots as well. You showed one video, the robot was moving over some small wooden planks.
Yeah.
Can it also burrow into them?
Yeah, sometimes it's okay.
Yeah.
But direction of the moving direction is not easy to control.
Yeah.
Because many obstacles.
Yeah.
And hits the obstacle, the changing the direction. So yes. So in the future, we should design that kind of autonomy to harsh the environment, automatically moving and desired position approach. That's a challenge.
With your haptics, where have you got your haptic sensors? Is it just on the fingertips?
Yeah.
With your haptic sensors, is it just on the fingertips, or can you cover the whole robot arm with your haptic sensors so that it can tell that it's up?
You say the question is related to what is soft robotics, right? And there are two types. One is that the robot is covered by soft material. Second is that motion itself is very soft. And my case is the second case. And this is, I said, I didn't say anything in that, but the contact task is just the impedance matching of the target and the robot. And target cannot change its impedance. So robot should change its impedance. And if impedance is matching, then you can just. And that is the meaning of the soft robotics. It's a my definition.
China?
So, show a video of the people who are highly successful. Yeah.
Yeah, okay. Yeah, so,
With the heterogeneity, the snake robot, I think it was the nuclear inspection. So, were there any considerations taken so the robot can actually survive in such an environment?
it's which environment?
The nuclear inspection environment?
Inspection?
Yeah.
Yes. So, for example, the inspection of the plant, tank, or some pipe, it is available.
So,
Yeah.
usually radiation also affects the electronics.
Yeah. In the Fukushima case,
Yeah.
protection for the radiation is very, very severe. For example, camera destroyed. Yeah. So that's another problem. So F-REI now study on that project developed a very tough radiation tough camera for CPU or something. So, Professor Nonami, do you have some comment for that's a protection for the radiation electric circuit
Yes, we are now,
devices?
yes, developing a new semiconductor, which is based on diamond or silicon carbide. So this is quite useful for not only strong radiation area, but also space, like a moon or Mars or everywhere. So this is a big market waiting for us.
Yeah.
I think your ACFR, your center, is mainly focusing field robots. So the ground robots, space, including space.
We are
I saw the
starting.
lunar.
Yeah,
Moon.
we're starting. Yeah, we're part of a consortium that will be building a lunar rover. Or going to the moon sometime this decade, apparently. We've done a lot of work already in, say, sort of analog space systems, so on Earth, but simulated space systems in sort of simulated Mars or lunar environments, student competitions, that kind of thing. But we're just starting, I would say we're just starting out in terms of real space robotics.
And the one thing, if you apply the F-REI challenge, and you will be going to winner, you can get some grant. Big grant.
Yeah.
So, yes, very, very challenge, exciting.
So another question on haptics. So you have that nice model with the 4 different elements of the haptics, but when a person is touching something, they rely on shear as well as force contact. Now, I noticed that none of your haptic systems actually relied on slipping. They just poke things.
Okay, I say that we have 4 elements.
Yeah.
And my system is estimating these 4 elements is within 1 millisecond.
Yeah.
So very high estimation process is necessary for this kind of system. And that means target impedance is identified, then a robot is adjusting his impedance much to the environment. And if this equation and this equation different, but if we have some contact task, then the equation is uniform. So equation is only one.
But that'll stop it crashing. So I know that's what your impedance does.
Yeah.
Your impedance, if it's grabbing something soft, it'll hold it and it won't crash it. But it still doesn't measure that it's going to slip.
Okay. The skipping is very different issues, and up to now I cannot solve this completely. But I believe that the change of the 4 elements is a kind of representing of the situation in target, including sleep. Okay.
Thank you.
And this my system is can have this kind of system if only 1 degree of freedom. And you can have, if it is very sleepy, then you can have this going down.
Yeah.
But you can feel going down.
Yeah.
Only one
Oh,
degree.
it'll change. Yeah.
Yes, yes.
Okay. Yeah.
So I believe that such kind of phenomena will be included in the controller in future. And I believe it's possible.
Okay. Thank you.
You're welcome.
I have a question about the those three terms. So you had the three terms depending on which were like sort of a mass, viscosity, and then a load term, right? The first three terms there, you had sort of one multiplied by j omega, one constant, one divided by j omega. You could also interpret that. That's also the three terms in a PID controller. Is that something that?
Okay.
Does that parallel be drawn? Are
of
people
course,
doing
definitely.
PID control by touch? Or?
But the PID parameters should change very rapidly, and it needs some kind of identification process.
Yeah.
So the equation itself is not important, but the process of the identification is very important. And maybe, for example, you can have again, this is very fast. So that this identification process inside the body is say less than 10 milliseconds, 5 milliseconds. And my case, it's almost 1 millisecond for very fast. That is, I introduced one chip here, and now I'm constructing one more chip. And this chip and this chip are cooperating each other. And this is controller and this identification, and it can work together, and you can have very nice haptic statements.
I guess I had a real broad question, probably to the first speaker. So about the research areas of the institute. So robotics are great to deal with the aftermath of the disaster, right? But in terms of preventing, is there also a humanitarian side to this whole thing? For example, when you deal with families that have to be migrated to other cities because of the disaster, or maybe because, well, I haven't read too much about the Fukushima disaster, but in terms of Chernobyl, for example, it was lack of transparency as well on the workplace. So is there kind of a work in that direction as well? So not even like something that's the engineering, but more like humanitarian stuff, because that's the point.
It's a very difficult question. I think the commissioning project is so long time, but now some area is trial and error robotics approach. But I think the features maybe more humanitarian access. Maybe it means so major mission should be replaced by robots like grasping and the reactor chamber is a very we don't know the real world. Nobody knows the inside of reactor chamber, So we just trying and error these days. So it's we need many technologies. So TEPCO is trying one of the approach like some robot hand, small robot hand to pick up debris. Small debris, 1 gram, that's all. And then we have the estimated volume would be 800 tons. Very huge debris there inside over a disaster chamber. So we have no idea how to access to pick up the debris. After pick up the debris, how to process to go to where, how. So we have no idea now. So the Japanese government is worrying about, and TEPCO is mostly worrying about. Very difficult question.
Any questions online?
No, I mean, no.
All right, well, let's thank our speakers again.